In this video, we will build on our model of the IEEE 9-bus system so that we have a look into the control of power systems. We will add dynamic models of the generators with automatic voltage regulators and governor models. This extended model will show how to control the dynamic response of the power system in the event of a disturbance. First, the automatic voltage regulators. The system that was created for the previous exercise is an uncontrolled system. You saw the effect of a load step event on such a system. To reduce that voltage imbalance, we have to introduce a control mechanism. Power plants generally employ automatic voltage regulators to control the generator voltage in an event of voltage change. An AVR is a feedback control system that measures the output voltage of the generator, compares that output to a set point, and generates an error signal that is used to adjust the excitation of the generator. As the excitation current in the field winding of the generator increases, its terminal voltage will increase. To introduce the AVR, we will need to make some additions to our existing generator model. Let us start with that. Open the generator workspace. Locate AVR Type 2 model in the Open IPSL library. Open IPSL, Electrical, Controls, PSAT, AVR, AVR Type 2. Now load two constant blocks from Modelica library. From Modelica, blocks, sources, constant. Name them as const1 and const2. Drag the AVR and constant modules close to the generator. Delete the existing connection between generator VF0 and generator VF. Make the following connections: generator V to AVR V, const1 Y to AVR Vref, const2Y to AVR VF0, and AVR VF to generator VF. Similar to how we introduced the generator parameters in the equations mode for generalizing the generator system, we will copy the same AVR code into the equations view of the generator model workspace before the equations section. For our convenience, we have already done so. Now in the diagram view of the generator workspace, open the AVR dialog and fill the text spaces next to the parameters name except AE, BE, VF state, VF00, VR10 and VR20. Note that parameter V0 is filled with V_0. Open the const1 box and name the parameter K as Vref0. Finally, set K as VF0 for const2. Save the model. After generator models have been updated, go to Network Model Workspace. Open any generator properties dialog box. It should now contain options to set AVR parameters as well. These values can now be populated for each AVR. The values for each generator are given in the tables section 2 of the modeling companion. Now that we have added the AVR, let us observe it in action through a load step event similar to the one we had in the last video. Keeping the same system with the load step, we simulate the network for 150 seconds. We will again observe voltages at bus 1, 2, and 3. As we can see, contrary to the last video where we had no controllers, the AVR helps to stabilize the voltage after the event, bringing it back to normal. The second part of the video is about governor systems. The frequency of the system is dependent on active power balance. As frequency is a common property throughout the system, a change of active power demand at any point due to generator outage or a load step will affect the system frequency. In the previous case, if generator frequency or speed omega is plotted, you will observe how the frequency is affected by the event. Because we have 3 generators in the system, there should be a way to relay the changes in demand to the generators. A speed governor on each generating unit provides primary speed control function, while supplementary or secondary control originating at the central control point allocates generation. Frequency control was detailed in the previous lectures, so we will not repeat the theory part here. The governor model used in this session is given below in figure 3 of the modeling companion. We will now add governor modules to the generator systems. Start by opening the generator workspace. Remove the connection between PM0 and PM. Now drag a constant block into the workspace and name it as const3 and set its value as 0. Locate the TGOV1 model in the DelMod library. Drag it to the generator workspace. Make the following connections: TGOV1 PMEC to generator PM, generator PM0 to governor PMEC0, constant 3Y to AGC input, and generator speed to governor speed. Finally, copy code block 5 in the equations view of the generator model's workspace before the equations section. For our convenience, we have already done it. In the diagram view of the generator workspace, open the governor model and fill in the parameters similar to the parameter names. This is also shown in figure 4 of the modeling companion. After the generator models have been updated, go to Network Model Workspace open any generator dialog box, it should now contain options to set governor parameters. The generator properties box open from Network Model Workspace is also given in Figure 5 of the modeling companion. These values can now be populated for each governor. The values for each generator governor are given in the table's section 2 of the modeling companion. Observe the effect of adding governor on system frequency using the same load event as before. Simulate the system for 150 seconds. For the governor systems, we would like to observe frequencies. So as we can see here, the frequencies recover post the event, while in the previous case, the frequency did not recover to a stable value.